school in Natal in 2023. And share my slides in just a second. Hold on.
Latin America.
If you all seeing my screen, yes, it's working fine. All right, so
are you on YouTube?
yes, yes, already live on YouTube. That's one of the series. So the Park and Astroparticles is based on the at the Federal University of Rio Grande do Norte. So this is sort of a series of events that we've been organizing since 2018. Organizing so we were participating of the Chernikov's, the CTA. The CTA school that happened in April this year. 23. So for those who are watching this, I welcome to apply to attend the Dark Matter Neutrino School and workshop that will take place in July next year at ICTP Safer in São Paulo, which we are also co-organizing with other very important members of the. Okay, so let's go. Without further ado, let's start. We're going to cover throughout these next 2-3 weeks to the evidence for dark matter. The second, we will 2 lectures actually. The fourth lecture will be related to kinetic decoupling. I think that even for the students who are in the room, they haven't seen any lectures regarding kinetic decoupling of dark matter so far. I've never talked about this in the past. And the fifth and the sixth lecture will cover direct detection. 2 lectures will go in depth in direct detection aspects and dark matter detection. The 9th, the dark matter complementarity, and the 10th lecture we'll discuss and cover some questions and so on that you might have. Okay, so if you have any questions, you just post them on YouTube. If you're watching through YouTube, post it there. We're gonna cover them later, okay, toward the end of the lecture. And these are the times, so you must have the organizers sent an email to everyone saying the dates and the time of those lectures. So she shared the YouTube links. In those YouTube links, once you click on them, you're going to see when those lectures will take place. So you just have to follow them. But obviously, you can just watch them whenever you want, given according to your agenda. So let's start. So today, I will discuss the evidence for dark matter. So that's a very introductory lecture. So I will not go in this school. I'm assuming that you're already familiar with dark matter, so you're not coming from. Okay, so let me just go straight. So in this lecture 1, we're gonna cover some evidence for dark matter that go from cluster of galaxies, galaxy rotation curves, CMB, BBN, formation of structures, bow, gravitational lenses, and collision of clusters. And so, hold on, let me close my WhatsApp because otherwise. And hold on, let me go back. My screen. All right, so there are several evidence for dark matter that go from small scales to large scales and also cover different time scales of the universe evolution. And that's why the evidence for dark matter is so compelling, because it's everywhere. And as I'm trying to convince you towards the end of the lecture, there is no alternative theory to accommodate the data and replace dark matter thus far. So the very first and famous one is related to Wiki. Zwicky and everything has to do with the something. To me, that's quite interesting. His paper was not at all and mistakes in the formulas, but still the message was correct. So let me try to address what the viewer theorem is and how Zwicky came to this conclusion that dark matter should be present in the coma cluster.
Just, Lucia is
Frozen?
it's frozen. Yes. It's frozen.
It might be okay, but I'm using the cable internet. So see? All right. But on YouTube it's correct. So the showing the right slide, right?
Yes.
Right? Okay. So let me go back. So the viewer theorem has to do with the following. So if you have a number of galaxies or stars in a given galaxy, or a number of galaxies in a cluster of galaxies, if those stars or galaxies form a bound system, then you can define a function psi towards the center of a given object times its momentum. The average in time of this function should be equal to 0. Then, well, if you apply the derivative in time of r and t, you divide this derivative. And then what happens is, once you know that the momentum is m times v, you're going to find, knowing that the kinetic energy is mv squared over 2, then you can relate the potential energy to the kinetic energy of a given bound system, whether are stars in a galaxy or galaxies in a cluster of. Either way, the average of kinetic energy of those individual objects are related to the potential energy of that object. In other words, just from this equation itself, you can conclude that if I somehow objects, I'll know the potential energy. And as you know, from physics basics 2, I guess, of the system. In other words, if I do know the individual velocity of the objects in the system, in the bound system, I can infer what is the total gravitational energy. In other words, if you happen to measure the velocity of the individual objects. So if you have the kinetic energy as number of individual galaxies in the coma cluster times their velocity, well, here I'm assuming, see, that all the galaxies in the coma cluster have the same velocity. Obviously, this computation should be way more complicated. You have the kinetic energy of individual galaxies, the total sum, and the total sum of the potential energy, you get the n squared. This has to do just with statistics. you get that the total mass of that system is given by the average square velocity of that individual object. In other words, so let's focus on that, on the physics part. The calculation is pretty simple. So if I do measure the average velocity of the individual objects, if they happen to have the same velocity, I know, okay? And here in this second slide, what I'm trying to these are simply extracted by the Doppler effect. So if you as the velocities of the stars or galaxies, in this case of the Zwicky is a galaxy, is receding or moving towards us, we have a Doppler effect, which will just shift the absorption lines. And through that, I can infer the velocity of that object towards us or receding from us. And knowing this, I know where the velocity, or for instance, knowing the lambdas, if the object is very close, this formula holds. So the velocity of the object is closely related to the of the absorption lines. Then I can infer the velocity of that object towards us. I would like to emphasize that this formula is not exact, it's just valid. Formula is not applied at all for a cluster of galaxies. You cannot use it, period, okay? This is only used for objects that have a redshift to us smaller than 1, which is not the case of the common cluster. So that was his overall conclusion was correct. No, it was, no, he just made it. The numerical result was wrong, but I would say the logic was correct. So what he found was, so he knew how much light was coming from the common cluster. So he for the total mass, m, and then he got this mass ratio of m over L equal to 400. I also should emphasize that in order to know the position of the common cluster, you should know the expansion rate of the universe, because that's how you measure how distant the objects are. And Zwicky used a H0 value, which was also wrong, his paper, but also in the calculations. But still, in the end, he found the overall conclusion was correct. So he analyzed, so that's the Vierer theorem. Vierer theorem is just something that in a bound system relates kinetic energy to potential energy. That's what the Vierer theorem is. And he found that the mass to luminosity ratio was about 400. What this number is saying is that you had the common cluster presented to have way more mass than should have the amount of galaxies he observed. For instance, the total mass they should have. But however, the velocity of the galaxies themselves was not what I would extract just given the luminosity. So in other words, I see a lot of mass through gravitational effects, but I don't see as. Therefore, there should be perhaps galaxies there. I just can't see them because they are too dim. They are not bright at all. I don't see them, and maybe it's making it's getting inducing a mistake in my calculation because I'm not seeing those galaxies. I'm miscounting them. But in other words, the mass over the luminosity was about 400. like off to you. However, for galaxies, they expected that whatever that had light would have the mass to light ratio was around 1 for galaxies. But this being 400 is indicating that you have mass that does not emit light. Therefore, there's some hidden mass in the Coma cluster. So for instance, that's what he says. Then he coined the term dark matter exists with a much larger, with a much higher density than luminous matter. I must say that his paper was not written in English. So that's tech. Okay, so his original paper was in German, but the translation of this paper is in this website. Anyways, so now moving to, so for instance, as you see, this was 1933. Okay, 33. Now we move nearly around 40 years to 70, when then Vera Rubin measured with her postdoc, Kent Ford at the time, measured the speed of 67 regions within these 3 to 24 kiloparsecs of the Andromeda galaxy. In the 80, they measured another ones. So for instance, they measured the rotation curves of 21 galaxies. So first, they measure the velocities of one in different points of one galaxy, Andromeda. Later, they measure the rotation velocity of different galaxies. So first of all, just one galaxy, and the other. So as you see, in the 70, you had one guy that made a mistake in some calculations, had used a different value for H naught, and he came to the conclusion that there was some dark. Another group, independently, 40 years later, using one galaxy only, came to the conclusion that would be that they needed something extra, such as dark matter. As you see, thus far, guy who made mistakes in the calculation, and two using one galaxy only, there was some. Show you the paper that they wrote in 1980. Let me open this paper. Not this one. Is this one? No, wait, one. Here, yeah. So that's the paper from Vera Rubin.
Excuse me, you're sharing the slide, not the.
Hold on. Sorry. Thank you. Okay, so let me share.
A new screen, and then share this.
Hold on, just a second.
You have to stop sharing and then choose. Okay, there you go.
Present slides. No. Present screen.
And then only sharing a window. So you have to share the screen when you go back to the slide.
So I have to share this. This one?
Yeah.
Okay. Let's see. But look at on YouTube how it's looking. Is okay?
It's okay.
Yeah, it's okay.
Okay, awesome. I'm sharing the whole screen. Okay, right. All right then. So that's the original paper from Rubin, Ford, and this Poor little guy, because he's never mentioned in any talk. I don't know, to be honest. So everybody talks about the Rubin and Ford. So maybe, I don't know. So that's the original paper. So as you see, in 79, let's say, it came to the conclusion is like this. So I'm highlighting here. Most rotation curves are rising. So let me zoom in. That's too much. But you can read it from there, right? Most rotation curves are rising slowly. Point. Nor low falling rotation curves. Must have significant mass image. So what they're saying is, I see a galaxy. Let's say my galaxy is around here. That's what I see. And they're measuring this point here, this point here. That's what I see. And this point here, this point here. That's what they're measuring, different points. And what they're seeing, that even those points beyond the ones that I can see where the galaxy is, they are rotating with a velocity which is nearly constant, which doesn't make any sense, as I'm going to show you using Mathematica. Even high school students can conclude that. Okay? So that's the first paper. So let me go back to my screen. Hold on. Oops. It's frozen? Yeah, it's loading. I can see. I know what's happening. It's switching from the cable to the... okay, now I turned off the Wi-Fi. Now it's only cable. It won't happen again. Sorry. And first now, like, welcome all of you who are attending the event. Newton is always present. Ana Vitória, Julia Mamprim, Mikael, Luca, and others. Okay. So see the whole screen or just me? But you can see me or no?
Yes.
You can? Okay, all right. And you can see the slides? As you see here, they were measuring one galaxy. That's the galaxy. Okay? So that's the one. There is no galaxy here. There is no galaxy here. There is no galaxy here. There is no galaxy. You can see it's located around there. So how come a point which is further away from the galaxy is even rotating with a velocity which is nearly constant? It doesn't make any sense. Therefore, there should be like some halo surrounding all these points. Systems are still somehow bound to the mass. Okay? And the paper that I was just showing you before from the 80s, it's 1979, where you had they had measured the velocity, the rotation curves of dozens of dwarf galaxies, or galaxies at the time. So see, obviously in the 80s the precision was not was very poor, and some of them have very weird behaviors. So for instance, they are rising here and then constant. This one has a bump and then goes like this. This one is rising all the time. This one is rising. This one rises, but all of them rise as you go further away from the center of those galaxies. So So for distance which is smaller than the radius of the galaxy, let's I'm assuming, well, doing spherical cows here. So I'm assuming the cow is spherical, or in other words, I'm assuming the galaxy, and which has a radius r. So I'm picking an object with mass small m, which is moving in a circle. Then the only force acting on that mass m is the gravitational force, Fg, equal to the gravitational force. So centrifugal force should be, well, I'm assuming it's a sphere there and has a constant density. Therefore, the mass of that sphere is equal to the density times the volume. The volume is 4 pi over 3 r cubed. Then, if you just plug in the number here where m is this, inside the sphere of any stars inside a galaxy should increase with galaxy here. And I'm picking a star here inside the galaxy. Let's say a galaxy is a circle. This star inside the galaxy should increase their velocity with the distance. So if I were to plot velocity over distance, and this is the radius of the galaxy, so as for r is smaller than capital R, the velocity should increase linearly with the distance. Okay? For r greater than capital R, capital R being the radius of the galaxy, they fall off with 1 over r, square root of r. In other words, I should expect that this curve should go like this. That's what Newton is telling us. Which makes no sense. Therefore, there is this big in red, data in red, and the theory is in black. So how come can you explain the data if your theory predicts a fall off with the distance? Okay, so you need something else. And how you can this is just an image so you can see it. So this is the galaxy that you can see. Let me zoom in a bit. So that's the theory. You can see there the theory, and that's what you measure. They are very, very, very different. Okay. Okay, and how? Look at here. Let me zoom in. So I'm finding that the v decreases with the distance. So if for some reason this m here, the total mass, and were proportional to small r, then the velocity would be constant. But how can you have a mass which grows with the distance? You've seen so far that the mass, for a sphere should grow with r to the third power. But you need to accommodate the data r that grows with r. Well, we know that this matter, whatever it is, has nothing to do with what we already know, because what we already know is that some mass with r to the third power, not with linearly with r. But that's what the data is telling us. So you either change your data, either change your theory, or you give up, because the data at this point, at this level, as you can see, that's in history. That was the very first compelling, really compelling evidence for dark matter. arguably, I would say that Zwicky was the first evidence, but it was not the very first compelling evidence because there were some mistakes and so on. It was just one object. But this paper from Rubin and Ford were compelling because it was not just one object, was not just one galaxy, were 21 that we need something beyond normal matter. Okay, all right. So, and here it is. So if you need a velocity which is proportional to constant, let's say the velocity, the mass of a sphere, assuming it's a sphere, that was my sphere, you integrate in volume of the density. But if my density, rather being constant, being proportional to 1 over square root of r, 1 over r squared, so my rho density is no longer constant, as I assumed before. It's actually a function of the distance. If that happens, then yes, my mass can be linear to r. As you see, nobody predicted that the density should fall off if 1 over r squared. The data told us that should be the behavior. Okay, so that was not the assumption, normal assumption. Okay, the density should decrease with the distance. That's what the data told us. So from this function alone, from this conclusion alone, just galaxy rotation curves, as you're gonna see later on, like in 6 lectures from now, that the density distribution of dark matter should behave something like this, 1 over r squared. Why? Because if you need to accommodate the galaxy rotation curves, that's what you should have. Period. Okay? There is no other way. And I'm going to cover this also in a lecture, what simulations tell us. Mass objects, so for instance, spheres in a cubicle, in a cube, and put small perturbations in the distribution of the matter in that cube, and let gravity take place. That's all. If you have a cube and you have a small bunch of matter distributed with a small, it's not homogeneous. If it were homogeneous, nothing would happen. With small perturbations in the density, those small perturbations should be the ones that CMB is telling us, cosmic microwave background. If you let that happen, just that, gravity will take place and will form structures like the ones you can see here below. And that's very low today. So what I'm saying, dark matter that has 1 over r squared. See, this rs is a constant. This rs is a constant, so let's forget it for a moment. So you have 1 over r squared. Okay, this rs is a constant, but I'm not going to cover this in detail. So if this is negligible, and this is a constant, you get 1 over r squared behavior, which is galaxy rotation curve is telling us. However, for galaxy clusters and so on, this rho profile is not precisely like this. It's a bit different, but very much like 1 over r squared, very close to it. And what I can tell you is that several independent groups have performed cosmological simulations to try to reproduce the distribution of matter in the universe. And they've all, if you do not include a matter that behaves like 1 over r squared, you simply cannot reproduce the data. Point. And that matter should not couple to photons, should not have electric charge. So if you want to something that reproduces the universe, should not have electric 1 over r squared. That's it. So, well, electrons, according to cosmologists, are baryons, and protons are baryons, and they do have electric charge. Therefore, dark matter should not be something at all close to baryons, which do happen. This is a paper, very nice paper. I have a list of references. Okay. But as I said, I will cover that later in more detail. So the one from CMB, to me, that's that was very compelling. So as you know, one thing that I should say that's very interesting, the Vera Rubin, for those who don't know, she was rejected at Princeton for being a woman. Is still frozen?
You can try to turn off the camera.
The camera? So let me.
There's no way to.
Yeah, I can turn off the camera. Hold on.
Okay.
I have to do. Audio has to come from my computer only. Hello, hello. Okay. My camera is coming from my webcam. Okay, now I can turn off my camera. Man.
Clicking on stop camera, yeah. Hello.
No.
Oh, Professor, over that right side, there, just for the screen. Over that right side, there.
Hello, 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 hello. Hello, hello. Testing, testing.
Yes.
Só que demora um pouco.
Okay. Working?
Yes.
Okay. All right. So Vera Rubin, after being rejected from the graduate program at Princeton because she was a woman, Harvard, and pursued her master's degree at Cornell, where her husband was a doctoral student. So Vera Rubin had a two-body problem with her and her husband. So she decided to reject Princeton and Harvard. So she was rejected from Princeton, and she rejected an offer from Harvard to be close to her husband at Cornell. But then she happened to have lecture with Feynman, so I guess it was okay. Anyway, and then okay, so moving on to the CMB. So I have to speed up because it's 10:40. So Arnold Wilson, okay, at the it was not actually a New York University, so was at is this? So they happened by the CB, just to remind you, is just the photons that are coming to us from the less scattering surface. Background photons decoupled from the plasma. And here it is. So to me, if someone doubts the existence of dark matter, they've never taken a lecture in CMB on CMB ever. At the first time I heard about dark matter, I said, "What the hell is this? Dark matter, man, this is crazy. Dark matter? What kind of matter is this? It's dark." But then once I learned, to me, was the CMB. The CMB like proved me wrong. Plots, panels are the difference in temperature of to us at different is just related to the angle at which the photons are reaching us. And this is the difference in temperature. So in other words, yes, the photons that come into us at different angles, they have slightly different temperatures, but almost the same. But interestingly, the abundance of the contents we have in the universe are related to the temperature of the photons that reach us. In other words, if I do happen to measure precisely the temperature of the photons reaching us, I can, with the same precision, determine the abundance of the matter and energy content of the universe. And that, to me, is sort of puzzling, but you can see in the figures. So what I'm showing here in the left, that was written from Chicago University. So what's showing here in the, here it is, and then you have the peaks. And it's showing, look what happened. Temperature in photons change in the universe and neutrons. If I change their abundances, that's what happened to the spectrum. Okay, as you see, there's a big shift. Okay, now if I just change now, not just the baryons, but the total amount of matter. So baryons plus, then if you change, again, you change a lot the power spectrum or the difference in temperature, delta T. See, the shift is huge. And the curvature of the universe also yields shifts the temperature, the delta T, towards the right side. In other words, as you see, I can look, the error bars, which are not shown here because simply you cannot see them because they are so small that you cannot see them. Coincide with the one in the bottom. As you can see, the curve, the measured curve is sort of this one right there in the bottom. It cannot be different. The error bar is so small that you can't see. Therefore, as you see, change the amount of baryons in the universe is very matter. And what, look, as far as we know, as particle physicists or cosmologists, the matter we know are made of atoms. Well, if the matter is made of atoms or baryons, omega matter is omega baryons, period. However, coincide. Therefore, I need something extra here. This something extra should not couple to photons. Should not. But how do you know this for compute the theoretical? So I'm assuming my model has something called baryons and has something else that does not couple to baryons. That's the assumption. If you assume that, you're gonna find that something else not coupling to photons, that's all the assumption, should be larger than the abundance of baryons. In other words, does not the ones that we already know. That's what CMB is telling us. And this is just a more quantitative statement regarding how the peaks precisely change according to the shift in the abundance of the elements. So this very first peak here, the very first height of that peak, it's called H1, depends a lot on the abundance of matter, depends not so much on the abundance of baryons, depends on a large amount to the cosmological constant, which is lambda, and the total amount of all the content energy budget of the universe, which is related to the curvature, K. In other words, you see, one peak is influenced by matter, baryons, cosmological constant, and curvature. But is driven mostly, as you can see here, by the constant factor, by the curvature of the universe. Just from this equation, because it was data-driven, you're going to hear in lots of cosmological talks that the very first peak of the CMB give us the curvature of the universe. It's not that's just sensitive to the curvature, but is the one that's mostly sensitive to the curvature of the universe. So the first peak give us the curvature. H2 is driven by the abundance of baryons, omega b, and the abundance of matters, omega m. The third peak, again, abundance of baryons and abundance. Everyone, even high school students, would know. I saw the internet going off and going on again. As every high school students would know, if I can solve the system, then I can know for sure, determine the abundance of baryons and the abundance of matter. I have two equations and two unknown variables. And that's how you can determine the abundance of matter and thought. And I'm going to emphasize before, at least in our group meetings. Look, so that's the pizza plot that you're going to see a lot in all talks. They say, look, the baryons comprise nearly 4%, 9% of the whole energy budget of the universe. Dark matter is nearly 70%, 27%, and dark energy, sorry, this is in Portuguese, and dark energy is nearly 68%. Okay, fine. But what about the error bars? Look at this. The abundance of dark matter is 0.12, but the error bar is 0.001. This accounts for less than 1% uncertainty on the abundance of dark matter. It's not that the dark matter is 27%, but could be 10, could be 8, or something. It's 27%, 20.6.8. So you're not gonna change from 26 to 30 or 26 to 20. You're not gonna do that according to CMB. This is less than 1% uncertainty in the data. So that's why you can come up with any gravity theory you can think of. That's what the data is telling you. Okay, and the BBN So BBN, I'll go faster in this BBN because it's more common. So what happened is, so if you have a gas or particle of non-relativistic particles, the number densities of particles in a given gas, non-relativistic gas, is Boltzmann suppressed. That's the Boltzmann suppression here, exponential minus m over t. What's m? M are the mass of the identical particles that I have in the system, in the gas. Okay? Therefore, if I am in a period of the universe in which protons and neutrons are non-relativistic, which are around BBN time, because the mass of the proton and mass of the neutron are around 1 GeV, and the temperature at which BBN takes place is way below that, orders of magnitude below that non-relativistic period. So that's the number density. This number density reminds by the volume. Temperatures GeV because they are non-relativistic. If you still non-relativistic, and the number density of neutrons and protons are close to 1. Okay, why am I assuming this? Well, I'm assuming that the temperature here is larger than the delta M. Delta M is the mass difference between protons and neutrons, which is 1 MeV. The protons is 1939, the one is 1938, if I remember, MeV. So 1 MeV difference. So if the temperature is much larger than 1 MeV, this ratio is close to 1. But in other words, in the early universe, we had equal amounts of neutrons cooled down greater and greater. And how do I compute that? Well, the relevant processes to calculate the abundance of baryons or protons and neutrons in the universe is just beta decay, neutron electron capture, neutrino capture, whatever. All is just take the beta decay, which is this one. Neutron goes to a proton, plus an electron, and antineutrino. And you move around. Should become a positron because of the electron conservation, charge conservation. Positron, proton plus charge plus, charge plus. Lepton number plus, lepton number plus. So then you can move around the particles. So I'm just saying that those who haven't seen particle physics courses in the past, that everything here is related to some quantum number. Okay, so what I'm saying, I'm doing some rough estimate here. So I'm assuming that the interaction rate, which is related to the cross-section, is proportional to GFT of the universe at that time. The H is the Hubble rate at that time, which is still radiation dominated, which is proportional to temperature squared to Planck mass. This is just a normalization, okay? So you have to, is just to remind you, the expansion rate of the universe is 8 pi g over 3, rho being the density of the material at the time. And then you can just relate the 8 pi g being the Newton constant with the Planck conclusion. When you compare the interaction rate, what is the interaction rate? Well, you have to compute the cross section of all these three diagrams here. You have to compute all of them. You compute the cross section of all of them, multiplied by the number density of those particles. That's what you get is the interaction rate, gamma. You know what is driving the expansion rate of the universe. So you know H. Then you compare those two. Why do you compare those two? Which is related to what we're going to cover in the next lectures. That's how you compute the decoupling of a particle. What is the decoupling? Well, if the always think as time. To me, it's very easy to think as a time. So what I'm saying is two particles interact with each other and the universe expanding. However, if the universe expands, then those two particles did not have time to meet because the universe expanded before that. So they decouple. This word decoupling means that simply they did not have the time to interact and then produce something, whatever. So that's called decoupling. Decoupling is just a time at which to the interaction rate, because from that point further in time, the interaction rate will ever be faster than the exponential rate. So you will always lose to the exponential rate. The exponential rate will grow much faster, and therefore these interactions will never take place, no longer take place. When you compare the interaction with the Hubble rate, you find that the freeze-out temperature is around MeV. What he's saying is that, look, the particle that's key in all these processes, here they are. So neutrinos are key to the BBN. If these neutrinos no longer interact with protons and neutrons around MeV, then these processes cannot take place anymore because they have decoupled. In other words, the decoupling temperature of the neutrinos is around MeV, which means that around MeV, these weak interactions are no longer effective. So therefore, you cannot convert a neutron into a proton. You cannot. So you cannot convert a neutron to a proton to a neutron. So if you can no longer do this, the only one which could be still be present no matter what is the neutron decay. The neutron decay does not care about this interaction, the very first two, because the only thing is needed is for the neutron to have enough mass to decay into protons, electrons, and antineutrinos. The neutron will always have that mass. Okay? So the neutrons will continue to decay into protons, neutrons, electrons, and antineutrinos. If the neutron becomes a bound state, then this decay is a free neutron, then this decay will always take place. Just simply computing these interactions, that's how you're going to see in books. So you have a neutrino electron, but actually what you're doing is computing wiki interactions processes. You find that, okay, at around MeV, neutrinos decouple. Therefore, as the universe cools down, neutrinos are no longer present in these weak interactions, where I have two particles and two particles in the initial state, two particles in the final state. Therefore, you don't have conversion of neutrons into protons. But remember, I can still have neutrons decay into protons, but protons can no longer be converted into neutrons. So neutrons, I have neutrons and protons in equal amounts. The universe cools down, and neutrons convert into protons through decay. Therefore, the amount to the amount of protons becomes greater and greater. What I'm saying is the number of neutrons becomes much smaller. The ratio and the number of neutrons compared to the number of protons becomes smaller and smaller. So that's the number what I'm pointing out here. So here below. So the number density of neutrons over the number density of protons becomes 1/6, around over 7 as the temperature. Yes, well, because at that episodes happen, but I will not cover them here because they are not relevant for dark matter purposes. But so let's assume so that helium-4 is comprised of 2 neutrons. If I assume that helium-4 is one of the most abundant elements we have and is one of the most stable elements we have in nature, if I assume, it's not correct, okay, but it's precise enough. If I assume that all neutrons end up forming helium-4, if all neutrons, then I can relate the number helium-4, which is about 1/25, 1.25. So 25%. So that should be the mass fraction or abundance of helium-4, 0.25. Where this 0.25 came from? I used that number, this one here, plug this number here into that. So at temperatures around 1 MeV, let's say a bit below, the amount of heliums formed were about 25%. Okay, so 25% of everything that made up baryons were forming helium-4 at that time. And helium-4 most abundant elements we have. We have other elements such as lithium-7, helium-3, but they have smaller abundances. What I'm trying to say is, let's say that I do this math, this simple estimate to calculate the abundance of helium, the most abundant elements we have: helium, deuterium, helium-3, beryllium, lithium-7, lithium-6, which are much smaller. And I compute all of them and I sum them up. So that'll be the total amount of baryons we have in the universe if I sum up the abundance of all elements. If I sum them up, I'm gonna hold on. Okay. If I sum them up, I'm gonna find the total amount of baryons we have in the universe, which is around 0.05. Omega amounts 100% of the universe is omega equal 1. 0.05 or 5%. So omega total obviously should be equal 1. I'm assuming the universe is flat, so it's 1. Only. There should be a large amount of something, of some, whatever that is. So BBN is not telling you how much should that be. It's just saying that whatever it is non-baryonic. Okay? But then I combine the two information. BBN is saying that baryons account for 5%. Fine. CMB is telling us that something which is not baryons account for 27. Therefore, there is a large amount of matter which is non-baryonic. It's not formed by inspired by dark. So that's when this dark matter name became really fancy, I would say, gluey at that time. And now let me cover one. I'm almost running out of time. Structure formation. So I'm going to cover this one, try to cover this one fast. The universe is homogeneous. If the universe is homogeneous, no galaxies will be formed at all. Because the gravity will cancel out each other, and no galaxies will be formed. In order for galaxies to be formed, you need some inhomogeneities in the matter density. And these inhomogeneities are parameterized by this rho 1. So you have a rho, which is rho 0, plus rho 1. Rho 1 is a small, very small. When you parameterize this perturbation in terms of a Fourier transform, and then you solve the Jeans equations, the Jeans equations tells you how, like a fluid, a density of a fluid evolves in time. So let's say I have a fluid in a sphere, and you have some matter here. But this matter suffers pressure in each other. So you have maybe particles in it here. They are moving with some velocity, v, random velocities, like in a gas. They're moving, and once they bump on each other, they'll create some pressure, okay? Because they bump each other, and they heat up like any gas. Okay. However, they have mass, these particles. So they have potential walls, or they are pulling each other through gravity. So if the mass of this particle, all particles have mass, so they feel gravity, 1. If these particles are slow moving, very slow moving, they do not cause pressure because they cannot moving slowly. If they have high velocities, they'll induce pressure. It's like a fluid. So if dark matter happens to be slow moving, if the particles that are made of dark matter are slow moving, they will not cause pressure on each other. They will just feel gravity. When you solve the fluid, so if you have seen a course on fluid dynamics, that's what it is. I'm just changing tension of the fluid or velocity of a particle in a fluid by velocity of the dark matter. And instead of being pressure, kinetic energy, I'm calling it pressure, like given the equation of state in cosmological physics. The Jeans equation. So this Jeans equation is telling us how the density of those particles in a fluid evolve with time. And then I solve it. And look at here. So that's sort of parameterizing how the clumps of matter evolve with time. So if that matter is dominated, the matter that forms my fluid is dominated by something as exerts feels pressure from the will oscillate in time. So I'm saying is if I have a matter here, let's say accumulated here, these photons will exert a pressure on the clumps of matter that had been formed. However, those baryons, if they're the one in blacks, they have electric charge, they will also pull the photons towards them. So it's like the photons coming in, hits the baryons, they spread out. But then the baryons have gravity, then they pull the photons back in. And these photons come, hit the matter, the baryons pull them back in, forms a fluids that goes back and forth. That's called oscillation. So they wash out, and they have matter, then they pull the photons back in. That's called, again later, baryon acoustic oscillations. So the photons will have a density which oscillates with time because they pull the photons back in and they are washed out by the photons. However, if that matter does not wash out them as effectively as this is like a fluid, right? So I'm not saying putting that as a charge there. We will not be washed out effectively as the baryons would suffer. Okay.
The equation is negligible.
Yes.
The term of interaction between radiation.
The pressure.
Yes, pressure.
They will not feel the pressure of the photons. And as a result, when then you solve the Jeans equations, then you find that the clumps of dark matter, something that does not feel pressure, here it is, pressure neglected. We are in the early universe. All the matter in the universe feels the photons is what they try to clump, the photons try to clump, the photons pass through them, wash them away. But there is some matter that I don't know what is it. The photons pass and they do not clump, and they clump as the time goes on. They clump with T over 2/3. Okay, that's in a period of the universe where the universe was matter dominated. And later, when the universe became matter dominated, radiation dominated, grows logarithmically with time. So what I'm saying is, so dark matter is always clumping as time goes on. But baryons, they oscillate with time because of the photons. The photons come in, wash them out. Photons come in, wash them out. They try to clump, photons wash them out. But there was a time in the universe which the photons were no longer around. That was when the CMB decoupled. So the free streaming of the photons became like infinite, very large. So the is very large, the size of the horizon. Pass through the baryons, it will be able to cluster now. But meanwhile, for a very long time prior to that, baryons, dark matter was already clumping and clumping and clumping prior to that CMB decoupling. Okay? And let's see what data says.
Now, can you go back to the equation, please? Because there in baryons says matter domination, so it should be radiation domination, right?
No, so one is matter, the other is radiation.
Right.
No, I mean,
he moved the baryon
at the side of baryon.
Indeed, it should be.
Oh, okay.
Mm-hmm. Yes. And even matter domination will be something we oscillate with time, but after CMB decoupled, then there's no such a thing.
In this case,
Yeah.
it should be something very similar to a plasma with matter and radiation.
Yeah, it's the same
working
thing.
together.
Yeah.
And not exactly separated with matter domination.
It's a fluid. Fluid comprised of different species.
Yeah.
And look what happened. So remember, at that time, around early 2000s, still the community that advocate for modified gravity theory will say, no, but still there is no evidence, compelling evidence for dark matter. Could it still be modified gravity? I must say this. So despite if people don't like it. So, not me. Look at this. This is a paper from this reference here, 13. Let me see, where is the reference? Here it is. It's a structure formation course. I like it very much. Look at this. So it says, let's think of this as time, okay? It's redshift, but let's think of this as time. What it's saying is this. So in the early universe here, in the early universe, it's hidden here somewhere, is growing. Then the clumpness growing. Until this point here, it's nearly one, see? It's nearly one. So there, one is homogeneous. the baryons and photons start oscillating. So that's it. This very beginning of the universe, okay, everybody's there. And then the photons start interacting with photons. Baryons start interacting with photons for some time, which is this period here. So baryons and photons were interacting. So photons will wash them out. They'll try to clump. Photons wash them out. The clumpness was just a... And they were growing. More matter would get more matter, more matter would get more matter, accumulating and forming structures. And at that point here, then CMB decoupled. Photons would now be able to free stream. Compelling. Well, because if we, then you say, how old are the galaxies today? This period. Fine. They are at this age. Should the matter be clustering? How long would it take for the... If they started from this point, they would not be formed. You needed matter, whatever it was, to be clustering way back then to have enough time to form the structures we see today. So you either come up with some dark baryons, whatever, but they'll still be dark. But baryons cannot cluster until this period here. So prior to that, they should have already, whatever matter should have already be clumping and clumping and clumping to form structures. And that matter, if it's not baryons, are just baryons. That's very important. This is the early universe. This has nothing to do with celestial bodies like planets and so on. This is early universe. And there is no such a modified gravity theory for early universe. This is not celestial bodies. This is like a quantum field theory, plasma physics. And then you say that plasma physics now is dictated by gravity? Modified gravity? No, come on. So modified gravities or theories are for Newton, celestial bodies, planets, and so on. In the quantum fluid world, the gravity is not the one that was a modified gravity is not relevant. Okay? So, and then let's say, another word to say is, the same theories that try to explain the galaxy rotation curves of galaxies cannot reproduce this data. I say, but for now, have people tried? Yes, they tried and they failed. But what if someone comes with a different modified gravity just to explain this data? Just this one. I want to come up with a theory to tune everything I want just to explain this data. Okay, fine, that's they did. So that's the one. So the data modified gravity theory just and the data is in black. That's how much cluster the modified gravity predicts. Different.
So where is the data in the first plot?
So this is the data. This PK is the matter power spectrum.
Yes.
How much in power the matter is clustering
Yes.
as a function of time.
But in the first one.
This one.
Yes. Where is the data?
The data is not shown. This is just is a lecture note. Would be some around here, something very like this.
Yes, that's what they were expecting.
That's what the data. The data would be something like this. So I'll say it's quite convincing. And Einstein is a guy who was a well-known physicist that advocated for modified theories. And he came up with another theory of modified gravity just to explain structure formation. And then Birkenstein is a professor from Berkeley University. And they asked him that could explain structure formation. And we've seen in many talks from people that advocate for modified gravity to replace dark matter. Okay, modified gravity can be relevant, but not to replace dark matter. Something different. So, okay, could you see if your model explains the data is not just a model? And then he hasn't done it. And then Scott Doddleson took his data, took his model, and faced with the data. And that's the figure that you see. That's done by Scott Doddleson. In blue, and the data is the one in red. The black line is just the best function that fits the data, the best function that fits the data. And you see the one in blue is a lot different from the data. Okay, so BBN is saying something. CMB is saying something. And Cluster of Galaxy would say something, but I will not have time to cover this now. So perhaps I'll pick up for the next lecture. And I'm gonna show you that many evidence for dark matter disfavor strongly modified theories of gravity. That Moon does explain nicely. But it's 1 month? No. For every galaxy, it's a 1 month. So we have 200 galaxies, we have 200 months. And then there's these 200 months. Yes, they are as competitive as dark matter. 200 modified gravity theories are competitive to dark matter in galaxy rotation curves. What about the rest? No, just dark matter. So modified theories are interesting, important to check, but not to replace dark matter. So I always want to emphasize this. So look, I'm not saying that, just saying that it's not suited for. So I'm not undermining your work. I'm just saying for dark matter is not the case, man. That's all. Okay. Okay, so we finished for today, and I'm gonna pick up from this point on, okay? Because I need to pick up my daughter at school. And I see you tomorrow at 9 a.m. Bye.